Title of my talk is Mpemba Effect and Ising model. Here is the outline of the talk. I'll give an introduction about what is Mpemba Effect, and then we'll introduce our system of interest, model and methods, followed by the observations and conclusions. So let us try to understand what is Mpemba Effect. According to Mpemba effect, a hotter system of water freezes faster than a colder one. For example, if you take two beakers of water, one is hotter than the other, and then refrigerate with the same thermal reservoir, you'll find that the hotter one will freeze faster than the other. And this counterintuitive fact was discussed in the time of Aristotle, and then many others have discussed the effect, like Roger Bacon, René Descartes, and others. And this was reintroduced to the scientific community by a schoolboy in 1963 named Aristo Mpemba, and that is how later this effect was known as Mpemba effect. Now, in the initial days, this was discussed in the case of ice-water system, and in recent years, there has been effort to generalize this effect. And this has been observed in spin glasses, granular gas, and ferromagnets, colloidal system, etc. So a common belief is that this effect is associated with the slowly evolving systems with complex energy landscapes. Now, we are interested in one of the simplest systems, the system that undergoes para to ferromagnetic transition, and we look at the presence of Mpemba effect in this system. Now, we consider the 2D nearest neighbor Ising model, the Hamiltonian given here, and this is a schematic of the protocol that we have used for the study. We first prepare the systems at different initial temperatures, say TS1, TS2, and TS3, and these are the structures corresponding to these different initial structures, and we quench these systems to a fixed final temperature which is below the critical temperature and look at how the system is evolving. So for this instantaneous quench, we use the Monte Carlo simulations with the Globus spin flip mechanism. In the Globus spin flip mechanism, you randomly select a spin from the lattice and then flip it and look at whether the energy of the system is decreasing or not. If it is decreasing, you accept the move. If it is not, then accept it with certain probability, which depends on the temperature. Now, by doing so, we looked at how the system is evolving towards this new equilibrium state. And here are the observations. So this one corresponds to the relaxation of the energy as a function of time from different TS values. Now, if you look, this upper panel in this plot corresponds to the early time behavior and the lower panel corresponds to the late time behavior. Now, if you look at this upper panel, you can see that the system which is having the highest TS value, that is 10, is having the highest energy. But at later time, this particular system is having the lowest energy value. So this means that the highest one is relaxing faster than the rest of the systems. Now, during this non-equilibrium evolution, there are formation of domains in the system, and this average domain's length, we denote it as L of t, and here is a plot of L of t as a function of time. And here also you can see that at late time, the highest average domain length is acquired by the highest initial temperature. So from these two facts, we can conclude that the system that are at the highest initial temperature is relaxing towards a new equilibrium faster than the rest of it. And this states that there is Mpemba effect in our system which undergoes para to ferromagnetic transition. This is the early time behavior and the ones. Yeah. So, okay, now one can calculate the times at which these energy crossings are happening by considering one of the energy curve as a reference point, and we call that quantity as TCF, and here is a plot of TCF as a function of TS, and these are plotted for two different reference temperature. So these are for 2.5 and 2.6, and you can see that there is a systematic decrease in TCF with the increase in the TS values. Now there are frozen states present in the 2D Ising model. Here are two different structures that one encounter at late time in the case of 2D Ising model. So if one encounters, at late time, if one encounters this kind of striped states, then the system will always get stuck into that. It will not evolve towards the ground state. So here we looked at whether the presence of Mpemba effect in 2D Ising model is the direct consequence of this presence of frozen states in the system. For that, we have excluded the configurations that are getting stuck in these metastable states. And here are the corresponding energy plot as a function of time for different TS values. And here also you can see that for the highest TS value, the system is seen to be relaxing faster than the rest of it. So it says that this frozen states are not the sole reason for the presence of Mpemba effect in the case of 2D nearest neighbor Ising model. Now, here are the crossing times again as a function of TS. And these red symbols here, that corresponds to the case when we consider all the configurations, including the frozen states. And the blue symbols here corresponds to the case when we exclude the configurations that are getting stuck in these stripe states. And you can see an overall decrease in the value of the crossing times here. Now we went back to the definition given by Aristotle. In a crude sense, it says that if water heats, then if we initially heat the water, then it cools down sooner. So we address the same scenario in the case of parato-ferromagnetic transition, where we consider two different initial temperatures, TS1 and TS2, above the critical temperature, and we heated the system from TS1 to TS2 and collected the non-equilibrium configurations during this heating process, and then quenched those configurations to a particular temperature below the critical temperature. And for the preheating process, here we considered the global dynamics and Kawasaki dynamics. So in Kawasaki dynamics, instead of the spin flip, we do a spin exchange. And this is used for the study of the phase separation in binary mixtures. So these non-equilibrium configurations during the preheating process, that can be considered effectively as systems with different TS values. And the final quench, instantaneous quench to below the critical temperature, that is done using the global dynamics. And here are the observations. So these are the energy curves, one from during the preheating process. This corresponds to the global dynamics, and the other from the Kawasaki dynamics. Now here this TG and TK, those are the time during the global dynamics and the Kawasaki dynamics in the preheating process. And we collect the configurations in between these during different TGs and TKs, and then quench these system to below the critical temperature, which is a temperature TF equal to 0.6 TC. Now, here are the relaxation plots for energy. And in both the cases, you can see that the one which is effectively at the higher temperature is going to relax faster. Now, so this implies that in both the cases, there is Mpemba effect present in the system. Now, one can look at how beneficial is ME in both the cases. So, interestingly, if you look at this global dynamics, and add up this preheating time to the instantaneous quench time, we can see that still the higher temperature is going to relax faster than the rest of it. Now, by looking for a possible reason for the Mpemba effect, the difference in the correlation length in initial structures can be one of the reasons for the Mpemba effect in these systems. But then an observation of the absence of Mpemba effect in the same model with the Kawasaki dynamics is reported by these set of people, and that tells that along with the correlation length, the associated dynamics is also playing an important role. With that, I'll conclude. We investigated the presence of Mpemba effect in uniaxial ferromagnet using 2D nearest neighbor Ising model. The system, which was quenched from higher initial temperatures, was approaching the new equilibrium faster than those started with the lower initial temperatures. This indicates the presence of Mpemba effect in the system, and a preheating process also supports the above fact. And the system that we considered does not have any glass-like energy landscapes, which makes the observation even more surprising. With that, I would like to thank my supervisor, Professor Subhro Das, and Koel Das, Shoini Chatterjee, Dr. Tanay Paul, and Shaumi Ghosh, who are working on similar topics, and JNCASR and other lab mates. Thank you for that.
One thing I was wondering about, the Mpemba effect in the original context, having to do with the stuff cooling, getting rid of kinetic energy, and becoming ice. that aspect somehow isn't going to be captured by Ising model by structural relaxation. You don't have the analog of kinetic energy in your problem at all, right? I mean, if you so in that sense, I just wonder whether it's fair to call all these observations of improved annealing if you start from higher temperatures, giving them all the name Mpemba effect. So I just do you have? I mean, could you imagine a study, let's say, where you took one of these magnetic problems and maybe included a Kreutz demon or something, you know, and
actually she has the setup already.
I see. Okay. All right.
Yeah. So, can I say something? Yeah.
The microcanonical ensemble we can consider and look at the path of. If we consider the microcanonical ensemble, then we can consider the path of how the energy is decreasing.
Partly a question of microcanonical, but I'm just wondering if you need momentum degrees of freedom also to really see the phenomenon in its full, you know, in a way that's properly related to its original context. I just wonder if you might need not just a configuration space picture, but a phase space picture. That's thought. Anyway.
So I would like to say what she added. Referring to the original Mpemba experiment, efforts have been to explain it via this dissipation of heat through boundary and all those things, Newton's law of cooling. But those are not very successful attempts, but more work needs to be done. And alongside, people started asking the question, if you make instantaneous coins, what happens? So this talk is related to that. And in addition to what you, the point that you have made, she already has the set of kind of thing.
But I mean, I still find this a bit surprising, that fact that you reach at same temperature in all cases, but after that it's going in different paths, right? At some point, it's everything, all the systems are at the same temperature because they're crossing.
Yeah. No, not temperature. It is an instantaneous one, so you cannot call it as at same temperature.
Okay, and temperature means you have brought it, you're running it at some temperature.
Yeah, to a fixed temperature from different initial temperatures. No, they are having different. Initially, they are having different energies, and
they are crossing.
Not
so. So you are talking.
Let's say just if you take two different temperatures.
Okay, these. So you. Yeah. So like basically this has to go towards a new equilibrium state which corresponds to the same energy. So if one is relaxing faster, then it has to cross the other.
Okay. But if I look at inside the system, I mean, they look different, or like the length scales are different. Is it
so instantaneously the length scales are different, and then finally they will go to the same value. One will saturate earlier than the other.
And the domain length at this point will be same. Like the cross.
The domain.
The corresponding domain length will also have the same.
No.
At that point they're different.
No, at the crossing times.
And at the crossing time,
it will be
different wall size. If you look inside,
that's a difficult question to trace, because whether the scaling. So there may be different fractality corresponding to the critical fractality of even after the quench. If that is different, for example, it's very difficult to say whether the length, how you calculate the length. You have to follow a particular convention. Okay. If one is more structurally looking different, different structures also can give rise to different same energy. So it's
okay.
But roughly, the asymptotic limit, wherever you start from, the structure eventually will become similar at some point.
Okay.
And we can discuss this point. It's
right.
complex.
Okay. Any other questions? I mean, the other question I already asked you before is like, I mean, if I do it in like at home, it never works.
But Rajesh answered.
Well, yeah, what was it? He said it's.
Then after that, I saw the movie. She collected the movie.
So if you like in the this cold countries,
somebody is putting
somebody's
bucket after bucket boiling water, and they're all
frozen and it become ice flakes and fall down.
immediately.
It doesn't happen if you look.
And this doesn't happen.
To do that normal water. Okay. Okay. So if there are no other, let's try.